So I'm Nick Adkins from the University of Birmingham, and I'll be the session chairman both this morning and this afternoon. And you can see the timetable that we have for different partners. In the project, the exploratory work covered a whole range of different areas. So there'll be people talking about the weld pool dynamics, the microstructural control and thermomechanical properties, the physical assessment of the materials. Quite a lot of work on developing the process for new materials, so for new alloys, and also interesting structures, lightweight lattices, auxetics, some work on shape memories and metal matrix. So you'll see presentations from the different partners in all of those areas. So this morning's session, we have, you can see in the agenda, we have quite a few speakers for this morning. And then at lunchtime, as we explained, there's an exhibition in the main foyer. And those people who are on the tour have to be with David for 1:15 by the front door. There's going to be some food up here on the mezzanine up here and also downstairs as well. So there'll be plenty of opportunity for refreshment. And then we have a few people talking this afternoon. And then we'll finish the final session. We'll finish in time for us to go downstairs and see the final sum up with David. So the first person to talk this morning is Filomeno, who's going to do his presentation now. There should be time for questions at the end of each presentation, so we can make this fairly interactive.
Thank you for the introduction, Nick. As Nick said, my name is Filomeno Martina. I come from Cranfield University. I've been working there for 8 years now, actually. It's funny because I was supposed to be there for a year, and then I liked this stuff so much that I never left. I won't have too long to present the work of effectively up to 4 PhDs. So I'm just going to give you a quick overview of our role in the project. And if you've got the desire to have more information, you can help yourself to the website where we publish things regularly. I will show you the link later. Or you can have a look at the papers which we are publishing, and hopefully we'll carry on publishing. The content of my talk will be split in 2 parts. The first one is about microstructural control into different materials. One is a titanium alloy, Ti64, which of course everybody is familiar with. And the other 2 are 2 aluminum alloys, the 2024, which is something that actually we developed in the form of wire and is not available commercially yet. And then the 2319, which is the equivalent in wire of the 2219 forged alloy. So first of all, what is WAM? WAM stands for wire pass arc additive manufacturing, which, as the name suggests, is based on the utilization of an electric arc to provide the heat, and then the feedstock is provided in form of wire. The beauty of this process is that so far it relies on standard, commercially available, off-the-shelf welding equipment, which means that the cost of buying a system can be very low, as little as maybe 40,000 pounds. And of course, we can go bigger and more complex, and much bigger and powerful machine can go up to 2 million pounds. It is a near-net shape process. So as you can see in this picture, I hope you can see from the back, the surface is not as pretty and defined as the powder bed additive manufacturing processes. Nevertheless, we are looking into replacing parts that are traditionally machined out of solid billets or very large forgings. And therefore, even if in this case you have to do a little bit of machining, as you can see from this very nice example, you are still saving a lot of material compared from machining all these pockets out of a solid block. Also, you can make parts much faster. So typically, lead times for forgings can be between 1 year and maybe 2 years. And we've made this part in a week as a research project, but in production it could be made in much less time. So that's the part how it looks after deposition. And then after machining, it's on the right-hand side. And if you remember from the video, you must have seen the part being rotated all the time. And that's something we like to do to exploit the symmetry. So in this case, there is an identical part on the opposite side of the plate, and that is to balance the residual stress. So each of the 2 halves of the component will have identical residual stress status in magnitude, but the direction is the opposite, and therefore the net effect seen by the base plate is 0, which means that the part will have no distortion when you unclamp it. And then what you see on the right-hand side is only one of the 2 halves. So after building, you heat treat, you split, and then you've got your 2 parts separated and without distortion. Also, we have recently made the world's biggest metal part. It's not a real component. It was a feasibility study towards a real component. It's 6 meters long and 300 kilograms in mass. And in fact, you can see it takes quite a lot of us to hold it. And the real part that we're going to make following this research is effectively a bulkhead for a fighter jet, which is 6 meters by 2. So that was just a study that we did last year. So why do we have to do cold work? What's the requirement for cold work? Well, if you're familiar with the microstructures developed by Ti64, for example, in this process, we know that the grains are very anisotropic. We've got components that are this big, and you can see the grains going all the way from the bottom to all the top. And this results in mechanical properties that are also anisotropic. Typically, in the vertical direction, the elongation is very, very good, but the strength is low, and vice versa in the horizontal. And then there is, of course, the problem of residual stress and distortion, which can be tackled by the symmetrical strategy, but sometimes that's not a possibility. And so when we unclamp the part, which are single-sided, the base plate will bend. From our experience in welding, we know that rolling introduces compressive stresses and eliminates distortion. And so we thought, well, it works so well in welding, let's apply it to additive as well, because at the end of the day, the problems are the same. So we tried, and then something rather unexpected happened, which is what I'm going to show you here. So again, recapping the control specimens with the big grains, and then if you do in-process cold work, which means doing a rolling pass every time you are doing a layer for the time being, the microstructure changes substantially. And so we go from a columnar configuration to grains that are much smaller, and they are equiaxed. And we have produced grains, in this case, I think as small as 70 micron in diameter. Then we also looked at the texture, and we saw that also the texture is changed. And you can see, first of all, the completely different scale bar. So these grains are actually much smaller than what you can see there. But the other thing you need to see is that in this case, the color scheme suggests that the grains are growing all in the vertical direction in the 001, and that also gives anisotropy to the mechanical properties. While in this case, as you can see, the colors are much more random, and therefore we could argue that the texture is much less than the control case. We also measure the residual stress, and you can see here stress is measured with two different techniques. In this case, we are using a technique called contour method, and I have to thank the chaps at Manchester University for doing the measurements for us. It's a destructive technique, but it gives you a contour map of the stresses throughout the cross-section. And so while diffraction method like those ones will give you just points, with the contour we can have a look at also to the thickness. And you can see that as we increase the rolling load, the tensile stress becomes gradually lower and much closer to a neutral state. Nevertheless, as you can see from that chart up there, even when we are doing rolling, so with the 50 and 75 kilonewton, stresses are still there. And that's because, differently from welding, if you are doing rolling of additive manufacturing structure, when you are deforming the structure from the top, there isn't so much constraint in this direction. And therefore, that's where most of the deformation happens. But if you want to relieve the residual stress, the deformation has to happen in this direction, that of the longitudinal residual stress. And so, yeah, it's very good for mechanical properties improvement, but not as good for residual stress. Anyway, it doesn't matter because we know how to tackle this problem, as I said, either with the symmetrical building or with very good tooling with which the part heat treated as a whole assembly. So, of course, then the next thing we did was checking the mechanical properties. And as you can see from this case, which is the unrolled vertical and unrolled horizontal, we are almost compliant to the specification for rod products. So we are definitely above the one for additive and cast, almost good for the rod. Nevertheless, we are still far from the current performances of the rod material. The very good news is that as we introduce rolling, this difference is reduced, and then finally for a rolling rod of 75 kilonewton, we are producing parts that have got properties that are even better on what's flying today. So we could argue that we can make parts that are cheaper, we can make them faster, and we can also make them lighter. I'm giving you two different data sets for 75 kilonewton because those parts were made on two different machines by two different operators with two different power sources, and they were tested in different places. And just goes to show that actually we can produce consistent properties also thanks to this addition. And the other thing you can notice is that the points are much closer to each other, which suggests that indeed the isotropic microstructure is also resulting in isotropic mechanical properties. So that in terms of strength, and then of course in terms of elongation, as you know from the hole-patch relationship, the elongation goes down as the grain size goes down. Nevertheless, we've got so much room until we go below the limit for the rod products that even with this big drop in elongation, we are still compliant to the standards. Just very quickly, some damage tolerance properties. In this case, these are specimens with KT 2.3, so the ones with the hole inside. And as you can see, when we introduce rolling, effectively for the same stress level, we are producing parts that have got 1 order of magnitude longer fatigue life. So that's in terms of KT 2.3, and that's in terms of fatigue growth rate. As you can see, even with the addition of rolling, we are still on the right-hand side of the rod product, which is very good news because it gives us confidence in terms of replacing these parts with others made with our technology. Now let's have a look at aluminium. At aluminium, the first thing we need to worry about is picking up the right waveform. So if you are using a MIG-based process, you have access to a wide list of synergic curves, MIG, Pulse MIG, CMT, CMT Advanced, CMT Pulse Advanced. So we had a look at all of them and characterize the microstructure from a porosity point of view. And you can see that with CMT, we do get a lot of porosity, as you expect in aluminium. As you introduce a variant called CMT Pulse, the porosity goes down. CMT Advanced porosity is even lower. And then finally, with CMT Pulse Advanced, the porosity has almost disappeared, which is great. However, when we do the heat treatment, which is required to increase the strength, the porosity reappears. And that's because the hydrogen comes out of the solution, and you've got the pores basically appearing in the microstructure. The good news is that if we are doing rolling in process, also when we do the heat treatment, the porosity doesn't appear. And that's because the solubility of hydrogen in this location is an order of magnitude higher than the solubility of hydrogen in the crystals of aluminium. And therefore, the hydrogen stays nicely in solution, it doesn't come out. And there is also another phenomenon called dislocation pipes. So some authors in the literature argue that actually the dislocations eventually go all the way to the surface, and therefore the hydrogen can actually escape from the parts. So in terms of mechanical properties, so this is the 2024, which is a Turner alloy. If you've got questions, you can ask them to Eloise, who's my colleague expert. I'm not even sure she's here. She's going to the room, okay. I'll take that back. So 2024 Turner alloy, aluminium, copper, magnesium. As I said, it was not available commercially, but we were able to get to the chemistry by feeding 3 wires in the melt pool. We knew what chemistry to get. We're feeding at controlled rate, and it worked very well. We fought extensively with editors that didn't believe that this alloy could be deposited without cracks, but actually worked. And then we went to the wire supplier with the recipe of the wire, and now they are making the wire for us, and hopefully they will also sell it commercially. And as you can see, similarly to the case of titanium, as you introduce rolling, the strength goes up, both the proof strength and the UTS. However, it doesn't quite get to the same level of the wrought alloy. The way we've got to get there and above is with the heat treatment. And okay, it's very nice to do heat treatments of this type on specimens that are very simple geometrically. Nevertheless, if you want to do this on something that is more complex, the chances are that you get distortion, you get cracking, and therefore, although it's good from an academic point of view, in practice, it might not be the best way forward. 2319, a very similar behavior, however, much less effect on the UTS in terms of addition of the rolling, and similarly to the previous case, we get properties that are much better than the wrought alloy, but with the temper. So I'm gonna go ahead and tell you what we can do to avoid the heat treatments in the next few slides. Now, the problem of top rolling, as I said, is that it doesn't restrain the material in the transverse direction. So what we thought we would do would be to use something called pinch roller, in which you've got 2 rollers that are going against the parts and are rolling in the direction of the travel rather than from the top. We didn't know how to implement this in practice because we actually didn't have the time to design the device. So the easiest thing to do to simulate this or to cheat in a way was to build a wall and then flip it by 90 degrees and then literally just roll it on the side using a normal roller from the top. And the idea that this works much better is demonstrated by the fact that when you're doing rolling from the side, the residual stress on average is pretty much 0. And in fact, with this method, we were capable of producing parts that had no distortion. The obvious drawback of this approach is that if you're coming towards an intersection, then you can't really go ahead with the pinch roller. And so again, there might be the need for a different process, and I will show you later. And actually, it's this one. It's what we call the pneumatic hammering. It's a very interesting piece of kit because, first of all, it can be attached to a robot, while the rolling, as you have seen from the charts, rolling requires a substantial amount of load, up to 75 kilonewtons, so the machine is really big and expensive. Pneumatic hammering can be done robotically because the load is minimal. The kit is very cheap. The tool can be as cheap as $5,000. And then, because you can do it robotically, you can explore all the 6 degrees of freedom of the robot itself. So you can process pretty much any geometry, and you can actually go deep in the intersections where normally you couldn't have access using the roller. So that's the way it works. In terms of characterization, to have as much clarity as possible, we applied it on machine surfaces, and that's just because we wanted to be sure that what we were seeing was the real effect of the tool. And the good news is that if you look at the residual stress plot that we've got here, it is very effective in introducing superficial stress. And in fact, this is the surface. This is 1 millimeter below the surface, and you can see there is a lot of stress, compressive stress, up to 1,000 megapascal in the case of titanium. In fact, the yielding compression is higher than the yielding tension, and so we can introduce a lot of cold work in this material using that tool. So this is very encouraging in terms of applicability of this process. Nevertheless, we shouldn't forget that when we do a rolling pass, there will be another layer deposited on top. And so what is really key is that the depth of what we remelt has to be smaller than the depth of what we could work. Because if we remelt all of this part, all of this goodness will go away. And that's what we're trying to understand now. The other implication of this process is that if you know in space applications, these days it's very fashionable to use laser shock peening to improve the damage tolerance properties of the surface. But laser shock peening is an expensive process. It requires big lasers, ablative paint, water. And maybe this would be a cheaper option to achieve the same results in a much easier way, actually. And this is just to provide you a comparison with the case of the surface rolling. And you can see that indeed, these compressive stresses are those introduced by the last rolling step, which is not followed by an annealing layer. And you can see they go as deep as 500 megapascal, while here we are much lower. And that's because the energy is much more concentrated in a smaller area. Then we did the same treatment to 2319, and it's striking how much porosity has disappeared thanks to this process. Now the question is, we don't know whether the porosity has just been squashed or actually the hydrogen is in solution in this case. Nevertheless, the effect is evident and promising. And as you can see, with the addition of the pneumatic hammer treatment, we can improve the hardness substantially. And then with artificial aging, it goes up even further, as you would expect. Now, going back to my point about the heat treatment, what we're trying to understand now, and we've got another PhD just starting on this, is can we push these trend lines farther up so to avoid the requirement for heat treatments altogether? And hopefully yes, but we will let you know. That was the part of the cold work, and now the second part is the one on the deposition of tungsten. I'm presenting the work of Gianrocco, who's with us in the audience, and he's about to finish his PhD, hopefully. So the first problem we had with tungsten is that, of course, it's got the highest melting point of all of them. And when we tried to deposit tungsten the first time, actually, I was doing that experiments towards the end of my own PhD. I was able to melt everything in the setup apart from the wire. And that wasn't really encouraging, as you would expect. And then we tried with the highest power of the lasers that we had, 8 kilowatt, and we were almost drilling another hole in the ceiling. So we were a little bit lost. And eventually we decided to go back to TIG, but with a key variation. Instead of using argon as process gas, we switched to helium, 100% helium. This automatically gave us 3 times the voltage, which means 3 times the heat input, and all of a sudden we had 10 kilowatt available, and that worked really well. And just to put things in context, this study on refractory metals is for nuclear fusion application, and David will follow after me and he will tell you all about it. Now, the first step, once we were actually able to melt the wire, was to get some stable deposition. And the problem of tungsten is that as the temperature goes up, the thermal conductivity goes down, and the electrical resistivity goes up. And in fact, that's why it's used for light bulbs. And the problem is that the effect of these two events is that you effectively are creating an insulating belt around the med pool. The heat builds up more and more and more, and all of a sudden, instead of building material, we are drilling holes. And that's a little bit defeating the purpose of additive. So we said, okay, we need to do something. And Gianrocco developed an advanced control system based on him looking at the screen and sloping down the current. And with this very advanced device, we were able to have a very nice and stable deposition, which then enabled us to build deposits that we could then characterize. So that's the first real part that we made. And critically, you can see here it was made on a plate which was flat. We abandoned this option immediately because we had cracks coming from the edges of the substrate. So the material was not cracking at all. Our material was good. The cracks were coming from here and then eventually traveling inside and then breaking samples. So what we did was flipping the plate by 90 degrees and depositing on the edge. So there were no open edges for the crack to start. And of course, I forgot to add the photo in the slides, but the specimen is downstairs. So if you go to our desk, you can have a look at the little component. Anyway, the good news is that we achieved 3 kilograms an hour of deposition rates. We were able to produce parts without cracks. There was no oxidation. We have tested some mechanical properties like the hardness, and Gianrocco has just finished building a lot of panels for the extraction of specimens for mechanical testing and thermal testing, and hopefully we'll have the results in the next few months. Then one of the requirements from the Center for Nuclear Fusion was to have a graded structure which had tungsten on the top to face the radiation coming from the core of the reactor, and then the underlying structure had to be made of molybdenum to give mechanical strength. And we were able to achieve a very nice gradient. Unfortunately, it happens over 4 millimeters of length, and the requirements coming from CCFE were actually for a 1 millimeter graded structure. So we're going to do some optimization of the parameters to see if we can get there. But again, it's very promising, and of course, the two materials like each other, so there is miscibility from a phase diagram point of view. So there was no problems with intermetallics or anything like that, which is, of course, making our life a lot easier. So that's it for me. If you want to have more information, go to wama.com. You can download a lot of presentation, papers. We pretty much upload everything we've got over there. If you want to have more information on the mechanical properties, there is a presentation recapitulating all of them, and everything can be accessed without any restrictions. So have a look. Thank you very much. Questions? We were using plasma. Yeah, we tried MIG at the beginning. The problem of doing MIG and titanium is that the arc wanders very much. The cathode spot emission is very unstable, and so you've got a very fast deposition in terms of deposition rate. But then your well bit would be all over the place. And so that results in problem when you're doing side-by-side deposition in terms of lack of fusion. And so plasma was the best way to go forward. And also plasma gives us much better control over the process because you can change current, plasma gas flow rate, travel speed, warp speed independently. While in MIG, everything is tied together, and so you can't really play much with the control, unfortunately.
And was it just locally shielded then?
In the video, yes, it was locally shielded. All of the mechanical properties that we've tested were also done on locally shielded specimens, and that's because you can't put a bag around the rolling rig, effectively. So we've been working on the shielding device for a number of years now, and in fact, I think we're going to start selling it next year. Yeah.
The hammering process that you have, is that done on every layer? And then how long does that take per square centimetre?
So it depends on the frequency of the tool and on the density of the heats. I think at the moment we're using 20 heats per square millimeter. Then you can apply the vibration in a variety of ways. At the moment we were using just compressed air so from the circuit, so it wasn't really too fast, but you can do it also ultrasonically. At the moment we are doing it every layer because of the depth. So if a layer is 1 millimeter and you are introducing 1 millimeter strain, you are forced to do that. Because rolling is much deeper, rolling goes maybe 6 or 7 millimeter in the material, rolling might not have to be done every layer. But we are not really here to optimize the process just yet. So yeah, we'll have a look at that in the future. All right, thank you very much.
Thanks, Falo.